About the nucleus and we look at what makes up the nucleus, we can look at these two pictures here, and we can see on the left hand side the nucleons are all together, the protons and neutrons, but then on the right hand side they're separated out. And so even if we have the same number of protons and neutrons, the situation over here on the left is different than the right. Now obviously we have electrons too over here, but apart from that, the nucleus is together over here, it's separate over here. And that actually makes a huge difference, and we're going to talk about that as we move now into looking at a little bit more modern physics, and this is very significant. So one of the things that is very important as we start to look at mass inside the nucleus at a very detailed level is the unified mass unit. And this is something you'll need to memorize for the IB exam. U, the atomic mass unit, is 1/12 of a carbon-12 atom. And so you take a carbon-12 atom and divide it by 12, and that is the unified mass unit. And so therefore, it'll be good to write these numbers down so you have these as a reference, and you need every single decimal spot with each of these, the proton, the neutron, and the electron, and the unified mass unit in kilograms. And this is the mass of a carbon-12 atom, and then divided by 12, and that's our unified mass unit, which we have there. So I would write all four of those down because we're going to use those to the furthest decimal spot as we take a look at what's happening in the nucleus. And this is very significant, like I said, moving forward here. Okay, and if we convert our electrons to unified mass units, we can do that. We have electrons in kilograms, and then we divide by our unified mass unit, and one U is this many kilograms, right? So this is the atomic mass unit for an electron. For proton, we can write this down as well. Be good to write each of these down. The unified mass unit for proton, 1.007276487, and then for a neutron, 1.008664891 U. So it turns out neutrons on their own are a little bit heavier than protons. Up to this point, we've just used one, but now we're going to need to go to a further decimal spot, because we're going to be looking at in detail what's happening inside the nucleus. So make sure you have each of these values down and on your paper, and so as we move forward you'll be able to use those. All right, so the mass of the nucleus. We take the mass of an atom and subtract the mass of the product and the number of electrons times U for the electrons, and we can get the mass of the nucleus. So the mass of this helium atom is 4.002602. We have 2 electrons, and we have the mass of the electron here. Multiply that by 2, and we can subtract the mass of 2 electrons from our mass here, and we get a nuclear mass of 4.00150,484 U. So that is the mass of the nucleus. So now what we can do is we can find the mass defect, and this is going to be very significant for us moving forward. What we do is we take the number of protons and the number of neutrons and get the mass. So let's go ahead and do that for here, and then we'll subtract the mass to get the mass defect. So the helium atom has 2 protons and 2 neutrons. The mass of 2 protons is, we take the mass of a proton, 1.007276487, and multiply it by 2, and we get this value. Let's get the mass of the neutrons. So 1.008664891 times 2. So that's the mass of 2 neutrons. Now, again, these are just on their own. So a proton here and a proton here, a neutron and a neutron, right? So not together. So the total mass of the protons and neutrons is 4.031882752. Now, what's crazy is if we take the nuclear mass that's listed there and we subtract that from the nuclear mass together. So the nuclear mass apart, which we just got here, there's 2 protons, 2 neutrons, we subtract the nuclear mass together. What's crazy here is we get a mass difference. The nuclear mass apart is this much. That's what we just got. The nuclear mass together is this much. It's not the same amount of mass, which is crazy, right? So if you think about this, you know, this looks like if it's violating the conservation of mass. The mass is not the same, right? And so we get this mass difference, 0.030377912 U, and this is different. You know, that's the difference in mass. That's crazy to think about, right? How could it be that the mass, you know, of these protons and neutrons apart are different than them just being all together like this, and this, and they're all together? So yeah, so that's another difference. If we separate the neutrons and protons out apart from each other, they have a different mass, and so that's crazy. So where's the missing mass? Well, we have mass energy equivalence. We can't just talk about mass on its own and energy on its own. What ends up happening is we arrive now at the most famous equation probably of physics, E equals mc squared. E is the binding energy of the nucleus. That nucleus is bound together, and that mass defect turns out that it's actually energy holding the nucleus together. And so, and we'll get the energy in joules here, and we can obviously convert to electron volts. It makes a little bit more sense. So let's go ahead and do that for helium. Our mass defect is 0.030377912. We can convert to kilograms, and then we get that in kilograms. We can apply equals mc squared. And that is the energy holding the nucleus together. That is the binding energy holding the nucleus together. And so when we convert to electron volts, this is the value of the binding energy holding that nucleus together. And so in that nucleus, there's an incredible amount of energy holding that nucleus together. And again, this is just for one nucleus. And look at the energy inside here holding the nucleus together. And so this is revolutionary, and this is a major factor here as we look at as we get into mass energy equivalence, where you really have to consider both. You can't just consider mass or just consider energy. You really have to consider both. So I showed this clip in class. I encourage you to search this in YouTube. This is Einstein explaining his equation of mass energy equivalence. It's kind of neat to see him explain this in his own words. So the mass defect, the mass of the protons plus the mass of the neutrons, is larger than the mass of the nucleus. And this is known as the mass defect. And that difference in mass is the binding energy holding the nucleus together. And it's the energy required to completely, the binding energy is the energy required to completely separate the nucleons of the nucleus. And so that binding energy is holding that nucleus together. If we could separate out those, that's how much energy it would take to separate them all out. So let's go ahead and try a sample problem here with oxygen. Let's find the binding energy of oxygen. And we'll go ahead and I'll kind of walk you through the steps here. So first we got to find the mass of the nucleus. So we have 8 electrons for the oxygen here, and we've got we multiply 8 times the mass of an electron, and that's the mass of electrons. We can get the nuclear mass by taking the mass of oxygen, which is listed here, 15.9994, and subtract out the mass of the electrons, and we've got the value there. And so now that we have the nuclear mass, we want to find the mass of the protons and the neutrons apart. So we have 8 protons and we have 8 neutrons. We multiply 8 times the mass of a proton plus 8 times the mass of a neutron. We get the total amount of mass for them apart, and then we get the mass defect. We take the nuclear mass apart minus the nuclear mass together, and we get a mass difference of 0.13251966 U. we can take that and convert our value into kilograms, and we get 2.20054,229 times 10 to the negative 28 kilograms. Pi equals mc squared, and we get our energy. We can convert to electron volts. And so, yeah, we have a major amount of energy here, holding this nucleus together. That is 123 million, almost 124 million electron volts holding this nucleus together. Okay, so I'm going to have you go ahead and practice this one. Let's find the binding energy of neon. And then we'll look at the second part per nucleon, but go ahead and practice at least right now the binding energy for neon following that same pattern. And when you're ready to check, you can hit play to continue. Okay, so let's see how you did there. We have 10 electrons here, and we can see that. 10 electrons, and we multiply the mass of electrons, so we get this is the mass of the electrons. We can subtract for the mass of neon, the electron mass to get the nuclear mass we have here. And then from there we get the mass of the protons and neutrons apart. So 10 times the mass of protons, 10 to the mass of the neutrons. And we get 20.15941378 U. Get the mass defects, we subtract the two. And this is the mass difference. Convert that into kilograms. And we've got our mass in kilograms, E equals mc squared. So that's the energy in joules holding this nucleus together. We can get that into electron volts, and there we go. So that's the mass that's the energy holding the nucleus together. So if we want it per nucleon, this is a really helpful thing if we want to compare one atom to another. What we do is we say, okay, how many nucleons do we have? Well, for neon here, we have 20 nucleons. So we're going to take this value and divide it by 20. And so that's how much energy per nucleon is holding the nucleus together. And so that can be, again, helpful if we're comparing different elements, because some nuclei have very large nucleuses and, have a lot of binding energy. And so this enables us to compare the different ones and how much binding energy each element has.